This is going to be a very quick recording on the color code, how to analyze the data. These are the resistors that I used, and these are the colors I came up with. And trying to analyze these here is looking at these numbers that I measured. And keep in mind, these are measured numbers. These are very close to the numbers that the resistors are rated for, but they're not exactly on it. So it may be 150 perhaps. This one here may be 240, this here may be 990, or perhaps 1000. There's a little bit of tolerance in there, which, by the way, I should give away. That's what the gold means. I don't think you would be able to figure that out just by looking at the resistors. The gold, so I have to give this away. The gold means that there is a 5% tolerance for resistors. So you could have something 1000 ohms plus minus 5%, which is plus minus 50 ohms. Okay, let's look at the colors here, the other colors. And I would say that kind of looks like this one here with the red, and then it says 220. Perhaps red means 2, and we can see that here 2 as well. There's a 2 there for red. Sure, there's a 2 here as well, but there may just not be enough space here to accommodate this 2, besides that this one is a measurement and it should be a rounded number to, well, perhaps 240, and that 2 really doesn't mean much. But this one here seems to mean something, the 200 here and the 220 here. So perhaps 2 means red. Well, if 2 means red, then perhaps 1 means brown. And then the brown appearing here in the third color band perhaps has something to do with these numbers being in the hundreds. And this number here, even though it does say 992, which is in the hundreds, admittedly, but remember there's some tolerance. Maybe that's 1000, actually. And then the red means perhaps that this number is in the thousands. So it would also have some kind of meaning, the 2 over the 1 here in the third color band. But as I said, this is going to be really quick, because if I go on here with any more, I would take too much away from your work. Figuring out the color code, after all, you will see, is really not that hard. This is for having a resistor with a battery, and I didn't use 390 ohms, I used 1000 ohms, because again, I don't want to take work away from students. So I'm going to cross this one here out. This is just going to be on my answer sheet here for my examples, and I better paste the ohm in here. So according to the color code, I should have used 1000 ohms, and I measured 992 ohms. Better not forget the unit. I measured a voltage of 3.24 volts. I measured a current of 3.39 milliamps. And then I compute the resistance according to Ohm's law, and that of course is voltage divided by current. And so that would be 3.24 divided by 0.00339, because it was 3.39 milliamps, so 0.00339 amps, and I come up with 956 ohms. Seems to be a little bit off, so the overlap between this number here and the measured number and the number given by the color code is not totally on, but still within those 5% that the gold indicates that the tolerance should be. The computed power is power equals voltage times current. So that would be actually 3.24 times 0.00339, and I come up with point zero, whoops, I can't see the number myself, 0.0110, I guess, rounded, and that would be in watts. Okay, for this one here, how is resistance measured? Well, as you recall from the video that I showed, you measure resistance in parallel to the resistor from the outside with no battery attached. How is the voltage measured? Well, also in parallel from the outside across the resistor with, of course, the battery attached, respectively, the switched on. How is the current measured? Well, wherever you want to measure the current, that's where you break the circuit open, and that's where you put the ammeter right in there and make it part of the circuit. This is 4 resistors in series. And again, I'm not using the same values that you find on your lab sheets because I don't want to take work away, but I use these resistors, and I better not forget that each of these numbers has a unit. These are all the numbers that were measured, and if we added these up here, the measured resistance, we in fact would come up with something relatively close. Let's see, 99 plus 149 plus 246 plus 473 comes out to 967. And remember, measuring this one here, this one actually is a computed result. I should also allow a box for this one little here, so that's what I should write down here, equals 967 ohms. According to the color code, it would be 250 plus 240 is 490 plus 470 is 960 ohms, and that seems to be really close to a 967 here. Okay, measured voltage. This is where the measurements. These here is the total measured voltage, and if we add up these numbers here, 0.31 plus 0.46, it's 0.77, plus this one here is 1.53, plus this one here is 3.00 volts. And then better make sure that I put the volts on here everywhere. Okay, this was the measured current, and then the computed resistance. Well, it's according to Ohm's law again. So R equals V over I, and for that one I'm gonna use the measured results, of course. So divide these by each other. So this is gonna be 0.31 divided by 0.00310 amps, and I come up with exactly 100 ohms. And then I do the next one, 148, and the next one, and the fourth one, and then I do the total as well. And those are going to be the numbers that I write in here. So that was 100 ohms. 148, 245, and 474, and 971. And as we can see, these numbers are all really close to what they should be. And then the computed power equals voltage times current, so it's going to be 0.31 times 0.0031 for the power and so on. Okay, that's the last result. Actually, that's the total. I'm going to do this on the side here, and then you can see what the results are. Okay, so that was the 0.00933, and this one I just calculated to 0.00096, and that's in watts. And this one is in watts, and this one I calculated to 143 watts. And then I noticed that actually I had accidentally multiplied here by I divided by 3.10 for the resistance, so by dividing by 3.11 actually comes out to 968 ohms, which is even closer to what I had measured. Okay, the last two results here. Okay. How do resistances add in a series circuit? Well, I kind of give it away with this one here, and of course with the numbers that we have seen here. In the series circuit, the resistors simply add. We can see that on these numbers here, we can see it on these numbers here, and we can see it when we compare these numbers. How do the individual, oops, that's actually off the screen, sorry about that. How do the individual voltages add in a series circuit? Well, you just add the voltages and you come up with the total respectively. You know, it's off by a little measurement error. Oh, that reminds me, again, I have to fill in a little box here where I will put in the computed one from the measured resistances. Okay, how do the individual currents compare in a series circuit? Well, they're all the same, going through any of the resistors.